This is Advanced Math, Chapter 12 on Vectors, Part F, page 3, in which we introduce vector equations. It even sounds cool. So we looked at this motion of a bird in a straight line on a piece of paper. So it's an imaginary bird. And we looked individually at how the x-coordinate of the bird changes with respect to time. And we looked individually at how the y-coordinate of the bird changes with respect to time. And we came up with two separate equations to describe that motion. An equation for its x position and an equation for its y position. So if we think about the x's and the x and y in this case as representing the position of the bird, we can also describe that position, that point in space, as a vector if you imagine that that vector starts at the origin and goes to the point where the bird is. So that position vector of the bird, that x and y position vector of the bird, changes as a function of time. And with the passage of every second, what you're doing is adding the velocity vector to the position vector for every second that goes by. So the x component of the velocity vector gets added to the x component of the position vector to get the new position x component. And the y component of the velocity vector is added to the current y component of the position vector to get the new y component of the position vector. And in this way, the position vector, second by second, changes as the bird moves. So this is not rocket science. It's just a sort of a compact way of saying this. A vector equation is a way of compactly expressing these two separate components, how they move independently, and writing it as a single equation. So it's more of a notation thing than anything else. So the example I have here symbolically in vector form is this, and it looks horrendous, but it's not. P vector that represents the position of the bird is equal to the velocity vector, which we wrote on the previous page, that was 3, comma 2, times the time, which is just a scalar, that's 0, 1, 2, 3, 4. So that's just getting that idea that every second that goes by, you're adding another one of these velocity vectors to the position vector. Also, when time is equal to 0, you want to say where you are. So when time is equal to 0, this is the initial position vector. So when time is equal to 0, this part of the equation goes away, and the position is just equal to the initial position. So this is exactly analogous to a y equals mx plus b equation for graphing a line. It's the position equals the rate of motion times the time plus an initial position. Just like for y equals mx plus b, the vertical position on the graph equals the rate of vertical with respect to horizontal times the horizontal position plus that initial vertical position when the x is equal to 0. So the role of each component of this y equals mx plus b equation is exactly the same as the role of each component in this vector equation. So these are really the same concept. But this, because it's hiding the x's and the y's and the z's inside each of these vectors. This works in two-dimensional space. It works in three-dimensional space. And if you want to get really freaky and talk about four and five-dimensional space, it still works. Whereas this is just, you know, boring. Okay, let's build up the vector equation for our moving bird. So the coordinates of the particle, think bird, when the time was equal to 0. That's the point, the very first point on that graph in the first page when the t was equal to 0. And that was coordinates -7, -4. That's our initial point. That's like our b on y equals mx plus b. Um, Now, if we're assuming that point O is the origin, then this vector OP, P0 rather, is the vector to this point, it's -7, -4. And when you start at the origin, your vector to a point is always the same components as that point. So this is just simply -7, this doesn't change at all, -7, -4. So that represents a vector. So if you imagine drawing a graph here and we have a point, this represents P0. The vector from the origin to P0 will have the same components as the coordinates of P0. So for example, if P0 was 3, 4, this vector would have components of 3, 4 as well, even though they really represent something slightly different. Okay, so our velocity vector we figured out in the previous page was 3, 2. We can now write in component form this vector equation. So the position vector is a vector that just has x and y as variables. So you just write it that way. Angle bracket x comma y. If you're in 3 dimensions, x comma y comma z. That's like the y equals mx plus b equation. Y is just y. You don't change it to anything. It's just y. So this is x comma y because it's in 2 dimensions. The slope, the rate of change of the position with respect to time, is our velocity vector. So that's the 3, 2 from here. And the initial position vector when time was equal to 0 is the last piece, and that comes from here, -7, -4. And that's it. That's a vector equation. Now I say it's a vector equation because the pieces of it, the dependent variable, the initial position, and the slope are all vectors. The only thing that isn't a vector is the independent variable, which is time. So when I say write a vector equation, well, that just means everything needs to be a vector except for that independent variable. And you write it just like a y equals mx plus b equation. That's it. That's it. Okay. Next page, I think we're going to be looking at, we should combine a couple pages. I'm going to start getting into some problem solving kinds of things. Alrighty. See you then.